Observe this transformation. A vector preserves its exact length as it rotates, eventually snapping into alignment with a principal axis. In basic linear algebra, these movements are easy to visualize. But when we transition to infinite dimensions, these same length-preserving and axis-aligning behaviors provide the mathematical framework for the entirety of quantum mechanics. To understand how, we must define the environment where these transformations occur. This is a Hilbert space, named for David Hilbert. It functions as a vector space capable of handling an infinite number of dimensions while remaining complete. The defining geometric tool here is the inner product. It allows us to calculate lengths and angles between vectors, providing a rigorous way to measure distance, even in abstract infinite-dimensional environments. Within this space, we use bounded linear operators. You can view an operator as a specific mechanism. It takes an input vector and transforms it into a new output vector elsewhere in the Hilbert space. This equation demonstrates a fundamental symmetry. If we apply an operator to the first vector in an inner product, there is a mirror equivalent. We can move that operator across the comma onto the second vector, provided we transform the operator into its Hilbert adjoint. By defining exactly how an operator relates to its adjoint, we can isolate three distinct classes of transformations that govern how space is stretched, rotated, or preserved. This algebraic relationship establishes a universal constraint that applies to a simple 3x3 matrix just as strictly as it does to the infinite-dimensional operators of quantum physics. First, consider a transformation that stretches space strictly along orthogonal axes, without introducing any scheming or rotation. This occurs when an operator is its own adjoint, meaning T equals T star. In functional analysis, we call this a self-adjoint operator. In finite dimensions, these are symmetric matrices if the space is real, or Hermitian matrices if the space is complex, named after Charles Hermite. Theorem 3.10-3 explains why this symmetry is so restrictive. In a complex space, the inner product of Tx and x must equal the complex conjugate of x and Tx. If the operator is self-adjoint, these two values are identical. Any number equal to its own complex conjugate has an imaginary part of 0. It is forced onto the real number line. This reality extends to the operator's eigenvalues. If Tx equals lambda x, then the inner product of Tx and x is simply lambda times the vector's length. Since the vector's length and the inner product are both entirely real, the eigenvalue lambda is forced to be real. It is this specific, undeniable mathematical certainty that allowed the physicist Werner Heisenberg to successfully use these operators to represent physical measurements. Because their eigenvalues are strictly real and their eigenvectors are orthogonal, self-adjoint operators ensure abstract quantum states yield the concrete, measurable data we observe in a lab. Now, consider a different goal, a transformation that changes a system's state, but leaves all distances and angles completely unchanged. This requires a unitary operator, where the adjoint is exactly equal to the operator's inverse. Multiplication of the operator by its adjoint results in the identity. In finite dimensions, these are categorized as orthogonal matrices in real space and as unitary matrices in a complex space. Theorem 3.10-6 formally proves these operators are isometries. If we simply look at the norm of the transformed vector ux and shift the u to the second term as an adjoint, the u and its inverse adjoint collapse into the identity. The output vector's length is identical to the input's length. The operator's norm is exactly 1. This makes unitary operators the standard for quantum time evolution. They allow a system to change over time while ensuring the total probability of all outcomes remains exactly 100%. If self-adjoint operators provide the measurement of a state, unitary operators move that state through time or between bases without losing any information. This leads to a broader question. What is the absolute minimum condition an operator must satisfy to be considered well-behaved and capable of being decomposed? The answer lies with normal operators. An operator is normal if it commutes with its adjoint. The order in which you multiply the operator and its adjoint does not change the result. Since self-adjoint operators are their own adjoints, and unitary adjoints are their own inverses, both classes satisfy this commutation rule. Every self-adjoint or unitary operator is by definition normal. However, the normal class is larger. Take the operator 2i times the identity. It commutes with its adjoint perfectly, making it normal, but the imaginary coefficient means it is neither its own adjoint nor its own inverse. Normal operators define the necessary boundary for the spectral theorem, allowing us to generalize the idea of scaling across a wide variety of transformations. To work effectively with these classes, we have to avoid several common analytical traps that arise when moving beyond finite matrices. First, do not assume the adjoint is always the inverse. This equality is the defining trait of unitary operators, not a general rule. Second, orthogonal matrices are a real space concept. In the complex Hilbert spaces used in physics, the unitary operator is the required generalization for preserving length. Third, the product of two self-adjoint operators is not automatically self-adjoint. Theorem 3.1-4 shows taking the adjoint of the product ST reverses their order to T star S star. The symmetry only holds if the two operators commute. Finally, Theorem 3.1-5 establishes that self-adjointness is preserved under limits. If a sequence of self-adjoint operators converges, the resulting limit operator retains the same symmetry. These rules ensure that the algebraic identity of an operator remains stable, whether you are multiplying them together or taking them to an infinite limit. This matrix summarizes the relationship between our three foundational operator classes. Self-adjoint operators are defined by equality with their adjoints. They yield real eigenvalues and orthogonal eigenvectors, serving as the mathematical basis for physical observables. Unitary operators equate the adjoint to the inverse. They function as isometries, preserving length and information during quantum time evolution. Normal operators provide the unifying rule of adjoint commutation, establishing the prerequisite for the full spectral decomposition of a system. These classifications allow us to determine if a complex system can be evolved through time without information loss, or if it can be broken down into independent, measurable components. If you are working through advanced mathematical texts like Kreyszig or Rudin, subscribe to the channel. We are building a library of visual explanations for every major theorem in the curriculum. What theorem or proof should we visualize next? Let us know in the comments. Next time, we will use these operator classes to unlock the spectral theorem. Thank you for watching.